So now that we have defined the determinant, we can start talking about eigenvalues and eigenvectors. To start with, these concepts, just like the determinant, are only applicable to square matrices. They could be complex matrices. We're going to restrict ourselves to real matrices, but the idea is at the very least they have to be square. So if you can find a real number lambda, again, that could in theory be a complex number, but for now we're going to stick to real numbers. If you can find a real number lambda and a vector x which is not the zero vector of Rn, such that a times x is equal to lambda x, where a is a square matrix, then you have found an eigenvector x of the matrix A and its corresponding eigenvalue lambda. So for instance, if you look at the matrix 3 minus 1 minus 2, 2, I tell you that lambda equals 1 is an eigenvalue of A, and it's an eigenvalue that's associated to an eigenvector. In fact, for a given eigenvalue, there's going to be infinitely many eigenvectors, but at the very least, there'll be one, an eigenvector 1, 2. Because if you multiply the matrix A by 1, 2, you will find, let's do it. So 3 times 1 is 3, plus minus 1 times 2 is minus 2, so that gives me 1. And then minus 2 times 1 is minus 2, plus 2 times 2 is 2. I get 1, 2. You notice here 1, 2, exactly the same as what I had to start with. So 1 times 1, 2. So this is your vector x. This is your vector x again. And this here is lambda. A times x is equal to lambda times x. In the special case where A is this 2 by 2 matrix, lambda is 1, and x is the vector 1, 2. Lambda equals 4 is an other eigenvalue of A associated to, amongst others, the eigenvector minus 1, 1, because if I multiply A by the vector minus 1, 1, I get minus 4, 4, which is the same as 4 times minus 1, 1. Lambda x, A, x. Well, the vectors 10, 20, and 17 minus 17 are also going to be eigenvectors of A. The first one will be an eigenvector of A associated with lambda equals 1. The second one with lambda equals 4. But what they are is linear combinations or multiples of the eigenvectors that have already been found. So yeah, they're different eigenvectors, but they're not really different in the sense that they belong to the span of one of the other two eigenvectors that have already been identified. Let's look at another example. Matrix A, which is 1, 1, 2, 2, lambda equals 0 is an eigenvalue of A, and it has an associated eigenvector 1 minus 1, because if I multiply A by 1 minus 1, I'm going to get 1 plus minus 1, which is 0, and then 2 plus minus 2, which is also 0. So here's A, here's X, here's, well, it's not obvious here when I'm looking at 0, 0. That's the 0 vector. But the 0 vector you can write as lambda times x, assuming that lambda takes on the value 0, and x takes on value as a vector of 1 minus 1. Very importantly, you might also say, look, I can write 0 as a vector here as lambda times 0, 0. So perhaps this could be the eigenvector. No, it cannot. by definition, an eigenvector has to be a non-zero vector. So you can have an eigenvalue, which is lambda, which is 0, but you cannot have the eigenvector be the 0 vector. Now, why is that useful? Why is it useful to have found the special lambdas and the accompanying eigenvectors? So you have a basis for Rn, x1, x2, all the way up to xn. Rn is n-dimensional space. A basis will contain n vectors, and linearly independent vectors. But let's say they're not just vectors, but they're the eigenvectors of some matrix A, and that they all have a corresponding eigenvalue, lambda 1 to lambda n. It's conceivable, you might see some examples, that the lambdas could be repeated. Like lambda 1 could be 4, and lambda 2 could also be 4. But this is not impossible. If you use the properties of matrix multiplication, then you can write any vector in Rn as a linear combination of these n eigenvectors, a1x1 plus a2x2 all the way up to anxn. And then if you multiply on the left by a, you get a times v, which would be the same as a times the linear combination. And because a as a matrix has linear properties when it comes to multiplication, that's the same thing as saying a times a1x1 plus a times a2x2 plus so on plus a times anxn. a1, a2, an, they're scalars. You can flip them with the matrix multiplication. This becomes the same as a1 times ax1 plus a2 times ax2 plus an times axn. And because xi was an eigenvector of a associated with lambda I, then you can replace each axi by lambda I xi. And so in fact, a times v is really lambda 1 times a1x1 plus lambda 2 times a2x2 plus lambda 3 times a3x3 all the way up to lambda n times anxn. Matrix multiplication, if you have the right basis to start with, you can replace it by a sum of scalar multiplications. And typically we find scalar multiplications easier to accomplish, easier to conduct than matrix multiplication. So okay, so how do we find these eigenthings? Like I showed you how you would verify if I tell you that lambda and x are eigenvalues, eigenvectors for a matrix A, you just multiply A by x and lambda by x and you verify that they're equal. But how do you find the lambda and the x? Well, the key is a chain of equalities, right? You're trying to solve ax equals lambda x. You want to find a solution here in x and lambda. Well, let's write it this way. Lambda x is the same thing as lambda times the identity matrix times x. I'm not specifying here, but this is the identity with n rows and n columns because we're assuming that A is an n by n matrix. And we can say that here because the identity has no effect when you multiply it by another matrix or a vector. Okay, so now I'm going to take the lambda ix and I'm going to send it over to the other side. And I end up with ax minus lambda ix equals 0. And here there's a common factor of x to the right. So I'll put it out. I'll extract the common factor. And I end up with a minus lambda I times x is equal to 0. Okay, so this is the system we're trying to solve. It helps to start by thinking of lambda as a fixed quantity in the sense that we don't know what it is, but it exists and it's fixed. It's not changing. So if you look at it this way, if lambda is some fixed quantity, then what you have here is a linear system. In fact, not just a linear system, a homogeneous linear system. The unknowns, the vector of unknowns would be the vector x here. We know as a homogeneous system that it has at least a trivial solution x equals 0, but we're interested in non-trivial solutions. So we would like for this system of homogeneous linear equations to have infinitely many solutions, so that one of them is non-trivial. One of them is not the zero vector. If the system only has a unique solution, then you have no eigenvectors. So lambda is not an eigenvalue. If the system has infinitely many solutions, then any non-trivial solution is going to be an eigenvector, and the corresponding lambda that gave you infinitely many solutions here would be the one you're looking for. Now, when you study physics, quantum physics, I'm going to do a little detour, you're going to discover a quantity called or at least a property called the renormalization property, which basically says that, a particle has a 100% chance of being found somewhere. So when you use physics, amongst other things, there's going to be an integral that should be equal to 1. But when you compute the integral, that integral can take on the value 1 only for specific values, specific energy levels. It's going to be something like this here. And in fact, there's a pretty strong link. That's the idea. Like, some of the values of lambda will give you here a system that has infinitely many solutions. The vast majority of possible lambda values, that almost complete set of real values, lambda will give you a system that has only one solution, the trivial solution, and hence it cannot be an eigenvector. If you look at a system of n equations and unknown, you know the system has infinitely many solutions if the coefficient matrix is not invertible, right? Because if the coefficient matrix is invertible, if you write a times x is equal to 0, and a is invertible, then you'll be able to multiply 0 and a times x on the left by a inverse, and you'll get x is equal to 0. So in order for you to have an eigenvalue, you need to have a system that has infinitely many solutions. In particular, the coefficient matrix has to be not invertible. And how do we know if a matrix is not invertible? Amongst other things, and there's tons of different properties here, but amongst other things, a matrix is not invertible if the determinant of the matrix is equal to 0. So you are looking for values of lambda which will make it so that the determinant of a minus lambda I should be equal to 0. The determinant is a number. In fact, if you have an n by n matrix, this expression here on the left is a polynomial of degree n in lambda. We call it the characteristic polynomial of A. Some people call it the eigenpolynomial of A. So, how do we find the eigenvalues of the matrix A? 1, 3, 3, 1. It's simple. We just look for the values of lambda which will make the matrix A, this one here, minus lambda I, be not invertible. And one thing I should mention, since this is a polynomial in lambda, and we studied fundamental theorem of algebra way back in chapter 1, we have always n roots to this polynomial. The eigenvalues are the roots of the polynomial. They could be complex, right? Because polynomials could have complex roots. So let's start by writing down a minus lambda I. What is that going to be? I, it isn't specified, but it has to be a 2 by 2 matrix if we want this expression here to be sensible, to have some sense. So A is 1, 3, 3, 1. Lambda I is lambda 0, 0, lambda. And if I do 1, 3, 3, 1 minus lambda 0, 0, lambda, I get a 2 by 2 matrix 1 minus lambda, 3, 3, 1 minus lambda. And what is the characteristic polynomial? I need to find the determinant of the matrix. The determinant of the matrix, well, in the case of a 2 by 2 matrix, it's quite easy to find the determinant. 1 minus lambda times 1 minus lambda minus 3 minus 3. Weird cross multiplication. So I have, let's do the expansion fully here. 1 times 1 minus lambda plus lambda squared minus 9. Or if you'd rather, lambda squared minus 2 lambda minus 8. We're expecting you to know how to find the roots of a polynomial, right? Using the quadratic formula, for instance. If what you have here is a polynomial of degree 3, we're expecting you to be able to find the factoring of this expression using synthetic division or some of the other methods you learned in high school. But you should be able to find these things. If the degree of the polynomial is too high, so for degree 5 and up, usually you use numerical methods. But even for the lower degree, ones 3 and 4, you might use numerical methods. At the very least, the ones we'll encounter should be easy to solve because they're either quadratic polynomials or the cubic polynomial with an easy root to find. Now this is going to be 0 if lambda minus 4 is 0 or if lambda plus 2 is 0. That's the factoring of lambda squared minus 2 lambda minus 8. So lambda minus 4 is 0 if and only if lambda is equal to 4. And it's equal, lambda plus 2 is 0 if lambda is equal to minus 2. There are two possibilities. In a 2 by 2 matrix, you should get two different eigenvalues. Now I say different eigenvalues, but they're not necessarily going to be distinct. Just that you're going to have potentially two roots that are equal. That's not impossible. The next little bit for you would be to verify that if I replace lambda by 4 and lambda by minus 2, sure enough, I get matrices A minus lambda I that are non-invertible. So A minus lambda I in the first case would be A minus 4I. So just replace lambda here by 4, and that gives me 1 minus 4 minus 3, 3, 3, 1 minus 4, which is again minus 3. And if you row reduce this, you will get the matrix 1 minus 1, 0, 0, which means that the rank of the matrix here is 1. 1 as a rank is smaller than 2, and sure enough, this matrix is not invertible. And so the original matrix was also not invertible. If you replace lambda by minus 2, which is the other root of the characteristic polynomial, you will get 1 minus minus 2 is 3, 3, 3, 3. Easy row reduction shows you that the rank of this matrix is also equal to 1. There's one leading one. And so the matrix A plus 2I is not invertible. And according to what we've discussed previously, any other value of lambda would give you an invertible A minus lambda I, so that you would have only the trivial solution to this system. And hence, this system does not have an eigenvector corresponding to the eigenvalue that you've picked. There's two exceptions here. Lambda equals 4, lambda equals minus 2. These are the ones we found by computing the roots of the characteristic polynomial. There cannot be any more because the characteristic polynomial is quadratic in lambda. Now the key bit for you here, I said it, but I'm going to say it again. The eigenvalues of the matrix A are the roots of the characteristic polynomial that corresponds to A, which is the determinant of A minus lambda I. The number of times, let's call that m lambda, that an eigenvalue lambda specifically appears in the factoring of the characteristic polynomial, that has a special name. It is the algebraic multiplicity of lambda. So what is the characteristic polynomial of this matrix A here, and what's the multiplicity of the eigenvalues? Well, we solve the equation where we set the polynomial equal to 0. What's the polynomial here? It would be, well, we have first we do A minus lambda I. And what is that going to be? That's going to be this matrix minus lambda times the identity. What does that give me? I get 16 minus lambda to 17, 0, minus 43 minus lambda, 14, 0, 0, 16 minus lambda. That's the matrix I get at the end. So if you want, I'll just make it easier by writing it like this. That is a matrix whose determinant is easy to compute because it is a triangular matrix. And when I have a triangular matrix, the determinant is just the product of the entries on the diagonal. So I get 16 minus lambda times 16 minus lambda times minus 43 minus lambda. Or if you'd rather, minus lambda plus 43. So I've taken the minus out of this and I just reordered the terms. And then lambda minus 16 shows up there twice. The eigenvalues would then be rather simply directly the elements on the diagonal. So 16 is there twice. So its algebraic multiplicity is 2. And minus 43 is there once. So its algebraic multiplicity is 1.